afternoon and welcome to the DVM student session of the 2020 Andy Lehman Virtual Swine Conference. My name is Pearl Judnitsky and I'm a faculty member at the University of Minnesota College of Veterinary Medicine. This afternoon, we will hear from 7 DVM students who are competing for the Morrison Swine Innovator Prize of $5,000. Please make sure that you ask them questions in the chat because answering question is part of their evaluation for who is going to receive the prize. Our first presentation is by Anthony Holoka from Lincoln Memorial University. Anthony is going to talk about preparing fecal microbiota transplant material for administration through a water medicator. Anthony, you may start.
Hello, Lehman Conference viewers. My name is Anthony Holoka, and today I'll be discussing my topic, preparing fecal microbiota transplant material for administration through water medicator. So this slide, I'll just kind of give a brief introduction of myself. In the top left corner, that very small state is called Delaware. That's where I'm from. Growing up, I was in 4-H, involved with sheep and horses. And I didn't actually see a pig until my senior year of undergraduate at the University of Delaware. This interaction led me to work at a research barn at the University of Pennsylvania before entering veterinary school. And this is where I fell in love with the pig. With my internship with Suidae this past summer, my interest has only grown. This summer I had the opportunity to see the swine industry during COVID-19, and I learned more about the pig industry than I ever thought possible. Meeting great people and leaders in the industry. And after school, I have a specific interest in using innovative technologies to improve the welfare of food animals, especially swine. So this slide kind of outlines the science behind fecal microbiota transplant. Then I'll go into my actual experiment and how I went about doing it. So first, FMT is similar to probiotics, but instead of delivering it through only, or instead of having only a few species of bacteria, FMT transfers all of the gut bacteria from one animal to another. And for GI-associated diseases, it does just that. It's associated with the restoration of normal flora. For respiratory neurologic diseases, it's likely more complex. So my inspiration for the study was Dr. Megan Niederwerder from Kansas State University, whose research is focused on the microbiome of swine. Dr. Niederwerder found that there was an association with disease resistance and gut microbial diversity in swine. Pigs that naturally harbored more species of bacteria in their gut were more likely to survive HERS infection. To test if the microbiome played a role in disease resistance, Dr. Niederwerder gave FMT to a small number of pigs, 10 pigs per treatment group, in a research setting, and challenged them with 2 viruses, PERS and PCV2. And this led to a result of 70 and 60% reduction of mortality and antimicrobial use, respectively, and which was related back to an association with increased microbial diversity. So it was that study that led me to design a project to scale up the delivery of FMT to hundreds of pigs in a large wean-to-finish commercial barn. Going forward, I tried to replicate Dr. Megan Niederwerder's methods as much as possible. First of all, I had to collect the sow feces, and high performance was the criteria for that was based off of her study as well. Feces was then processed using a protocol developed for human FMT, which included dilution, blending, filtration to remove large particulate matter. Unlike Dr. Niederwerder's study, which delivered FMT through a oral drench, I chose to deliver FMT through a water medicator because of the large amount of pigs in my study. The pigs in my study received the same amount of FMT solution per day in drinking water that Dr. Niederwerder's gave as an oral drench. So my design was built on her original study, but it was scaled into a commercial wean-to-finish barn setting with 1,200 pigs in each treatment group. So the idea was basically taking that FMT solution and over 1 week period, administering it through a water medicator, just like you do your normal water medication drugs. So the first step was collecting the feces, and the collection criteria was based off of Dr. Meghanito's criteria, which included lactating, parity greater than 6, average board alive greater than 14.5, average mummy less than 1, number weaned greater than 11.1, and 34 pounds of feces was manually excavated, bagged, and then immediately frozen on dry ice and stored in a negative 23 Celsius freezer. And this took me 4 days to do this process, to yield a final result of 20 gallons of FMT solution after the processing steps. So the first step of processing was taking the 34 pounds of feces, homogenizing it using 250 milliliters of saline glycerol to 50 grams of feces. And this solution was again based off a Dr. Niederwerder's study, which was a step in the human FMT literature. But the saline glycerol solution, besides its diluting use, was to provide safety for the bacteria in the solution when frozen. Next was straining, first through medium, then a fine cheesecloth, just to get rid of those large particles so it would go through the water medicator easier. So the final product, you can see here on the left, there's a large pooled solution here. And this was in a 30-gallon bucket on ice. We took a pooled sample, not only for diagnostic testing, but also for microbial diversity analysis. This was then bottled into 42 individual liter bottles, 6 of which were given daily for 7 days, which led to 5 mils per pig per day getting this solution. And this was also the number that Dr. Niederwerder's study did. The end result led to 6 liters of the solution per day, and it took about 9 to 10 hours for this to be consumed. And this is about what would be expected for any water medicator solution to be consumed by pigs. And you can see here with my mouse, the light brown solution here, that's the solution actually going to the water medicator, diluted 1 part to 128 gallons of water. So this this black cord represents the water pump that's keeping that solution stirred throughout the day. Okay. So implications for the swine industry. There are many possible routes that this idea of FMT could take, but I'll focus on the more important implications. The important thing is that this process was converted into mass administration, just like any water medication that's currently used. Firstly, possible implementation into normal health protocols. So addition to or replacement of antimicrobials and anything in between. This is important for the ever-increasing desire in the industry to reduce the amount of antimicrobials used. It's also important because overall, besides the time factor, FMT is very inexpensive to create. Talking about prophylaxis and treatment, prophylaxis, the idea is FMT gives these piglets a fighting chance because it gives them the best possible selected bacteria, gut bacteria from the highest performing sows. And then going forward into treatment, based off of Megan Niederwerder's studies, FMT has a significant effect on disease challenged animals. So this could be an amazing prophylaxis, an amazing treatment for production animals, especially pigs. Going off of that, there needs to be a streamlined preparation of FMT for mass production. And this is something that could easily be increased. Just increasing the amount of seeds that you use and the amount of materials could definitely decrease the amount of time and effort put into creating the solution. Finally, there's more data that needs to be collected for the best choice of donor fecal material. And this could be taking nucleus animals, the highest performance sows, that's what we need. But overall, the options are truly endless for the research and implementation of FMT in the swine industry. This is an acknowledgement for everyone that was involved. I want to thank Suidae Health Production, which was my host, and Elanco, which was my sponsor, and Iowa State for the SFIP program, of course. Thank you.
Our next presentation is by Erin Kettelkamp from the University of Illinois. Erin is going to talk about the effect of particle size and H2O2/PAA concentration on the efficacy of an aerosol decontamination system for items entering swine farms.
Hi everyone, my name is Erin Kettelkamp and I'm a fourth-year veterinary student from the University of Illinois. This summer I had the opportunity to evaluate the effect of particle size as well as hydrogen peroxide and peracetic acid concentrations on the efficacy of an aerosol decontamination system for items entering swine farms. In terms of aerosol decontamination, that's often implemented through the use of foggers. And the goals of these foggers is to quickly and completely disinfect items entering swine farms to reduce the risk of pathogen entry. The reality is, according to recent studies, is that commercial foggers result in an incomplete disinfectant contact to all sides of those objects. Therefore, manipulation of objects is required to complete disinfectant contact. For the aim of my study, I wanted to ask a couple of questions. The first being, does aerosol particle size matter and impact fumigation processes? And what effect does concentration of disinfectant have on the efficacy? For the use of this study, I used a proprietary blend of hydrogen peroxide as well as peracetic acid. For the low dose of those active ingredients, Actril, the ready-to-use formula, was implemented at using 200 milliliters. In order to increase that, a concentrated formula of Mincare solution was used at the equivalent dose of hydrogen peroxide and then double the dose of hydrogen peroxide with increasing peracetic acid concentrations. Each of those was diluted to a volume equivalent of 200 milliliters. In order to compare those active ingredients with just an active ingredient of hydrogen peroxide, we use intervention within this model as well. There are many benefits of using the hydrogen peroxide and peracetic acid blend. First, it's fully biodegradable and will dissociate completely to vinegar, oxygen, as well as water. This happens to be human and food safe with no toxic aldehyde vapors and is much less corrosive than those aldehyde-based products. It also will not leave a residue and is registered by the EPA for the use in pharmaceutical clean rooms. When I'm discussing the differences in droplet size, I want to orient you to this visual model here that's a good scale effect of what we're trying to accomplish. So our dry fog, all the way on the left, is going to be a particle size less than 10 microns. Our average measured was 5.9 microns through a nozzle at 75 psi using an air compressor to create a uniform droplet throughout the room. Next category would be our fine mist, anywhere from 10 to about 100 microns, and this is where our hurricane fogger comes into play. At the low flow rate of those hurricane foggers, you'll emit an average of about a 14 micron droplet. This is used for our mid-sized droplet in this study. And then for our larger droplet, we cranked up the hurricane fogger to the high setting, and that'll emit a particle size average of about 26 microns. This is actually very important because what I've found is that the dry fog particles are so small that when they're emitted from their source, they permeate around the room, and actually when they hit a solid surface, they bounce instead of bursting. And so they will come in contact with multiple surfaces throughout the time that they are aerosolized. You compare that to a fine mist particle that once it's emitted, it rises and falls under the forces of gravity, and when they hit that solid surface, they're actually going to burst, and that is how their disinfectant contact is effective. My treatment room model was relatively simple. I placed 2 boxes in the center of the room, raised them up on the top of a wire cage. On box A, I placed our biological indicator strips, which I'll go into more detail about later. Box B's purpose was simply to shadow box A, and our fogger was placed also in the center of the room, just adjacent to the boxes to maximize the permeation effect that could be emitted from that fogger. At points A through D, hanging in the center of the room, those are our relative humidity sensors that were able to measure the humidity curves before, during, and after treatment. For our sampling process, we opted to use these Geobacillus biological indicator strips with population counts of both a log 5 and a log 6 on these boxes. We use them because they're the standard for validation of a dry fog system in those pharmaceutical clean room settings. They're also very resistant to decontamination, more so and more robust than any of the other bacteria or viruses that we'll be exposed to in the field. During treatment, the room remains airtight and was remained sealed for 1 hour post-treatment when all disinfectant was emitted into the air. After treatment and after 1 hour, the biological indicator strips were transported back to the lab for culture and incubation. And inside those strips, there's a small disc that has a concave platform where the G-bacillus populations are able to reside. And those are placed into our broth tubes that have a color indicator. And so the purple clear tubes there at the bottom, those are negative for bacterial growth. But when they became yellow and turbid, those were considered positive for bacterial growth in our results. And what we found over the course of the results is that there was actually a multifactorial effect where particle size was significant, but so was concentration of the hydrogen peroxide and parasitic acid that we used. Going from left to right here in the data, we found at the small droplet size, or the dry fog that is, the high dose of MinCare was most effective, where we were able to achieve a log 5 reduction on 100% of the sides and a log 6 reduction about 94% of the time. We compare that to the intervention, however, which had the same concentration of hydrogen peroxide, but with no parasitic acid, and we received no decontamination of any sides of those boxes. When we increased our particle size, our high dose of the MinCare solution was still the most effective. We were still able to receive a 100% log 5 reduction on all sides. We had drastically lower log 6 reduction rates. When we increased our particle size yet again, we noticed a significant loss in percent decontamination rates. When we break this down by sides, this is the same data presented per replicate, and what was critical here to note was that the top of the box was always the easiest or first side to be disinfected, with variable effects on the other sides of the boxes. The bottom of the box was always the hardest to decontaminate, and that was always our goal, to reach the bottom of the box, which was consistent with our log 6 box side reductions. Whenever we could achieve disinfection rates at the bottom of the box, that was always our indicator as to whether or not we were effective. To validate what our log 5 and log 6 bacillus reductions meant, we also plated PERS MLV onto sterile petri dishes, and I placed those onto the sides of the box and subjected those to treatment as well in conjunction with our biological indicator strips. What we found was any side that we received a log 5 reduction, we also received PERS inactivation. Regardless, and this was also regardless of our log 6 reduction rates on each side of the box. We also implemented organic material, or a manure slurry, that was plated onto petri dishes as well. And just like our PERS model, any side where there was a log 5 reduction in those geobacillus indicator strips, we also had decontaminated our organic material, as indicated in our swabs there compared to our positive control that was turbid and positive for growth after incubation. These are very promising conclusions, and so our effective aerosol decontamination model is possible on the farm without having to manipulate items during treatment. Complete object disinfection rate definitely requires a droplet size less than 14 microns. For most optimal disinfection rates, droplet size should be less than 6 microns, aka a dry fog. Hydrogen peroxide and parasitic acid concentrations are also critical and should be used above 4.2 and 0.13 parts per million, respectively. I would like to thank the team at the Applied Epidemiology Lab at the University of Illinois for all their help with this project. And thank you for listening. During the live session, I'd be happy to answer any questions that you may have. Thank you.
Our next presentation is going to be by Chris Kovac from Iowa State University. Chris is going to talk about evaluation of the finishing mortality removal process and factors that contribute to contamination spread.
Hello, my name is Chris Kovac, and I'm a second year at Iowa State University, and our project evaluated the finishing mortality removal process and factors that contributed to contamination spread. Rendering trucks can pose as a biosecurity concern, as these trucks have the potential of introducing pathogens onto a finishing site. And without the proper biosecurity protocols in place, cross-contamination during mortality removal can occur, further enhancing the risk of introducing diseases into the herd. With that said, the objective of the study was to evaluate the mortality removal process on different style finishing sites using fluorescent powder, glow germ, to determine what associated factors contributed to the greatest amount of contamination spread, and whether implementing various biosecurity protocols could reduce potential disease introduction from on-site rendering boxes into pig spaces. This was an observational study using 4 4-ounce bottles of fluorescent powder, glow germ, in conjunction with 1/4 bottle of fluorescent lotion, which was then spread within a 90 centimeter by 70 centimeter grid constructed out of PVC pipes, which is shown in this picture, and each site was set up in the same manner. And different sites were chosen based on method of mortality removal being conducted, and specific areas on these sites were categorized as low risk, which was the dirty side of the office entryway, dirty side of the bench, moderate risk, which was the clean side of the entryway, clean side of the bench, and high risk, which was inside the pig space barn. Caretakers were also blinded and unblinded to determine if any bias from that would alter the spread. A UV light was used to observe the glow germ, and various mortality removal processes were compared to determine what method and vectors contributed to the greatest amount of spread. So risk assessment areas were categorized as high risk, moderate risk, low risk, based on the likelihood of introducing disease into the herd if a pathogen were to be found in these zones. So in the high risk areas, we found glow germ in the alleyway, on the gates, and even on the pigs themselves inside the barn. We also found it on barn boots. In the moderate risk areas, we found it in the office, on coveralls, gloves, in the shower, and even on the bench itself. Within the low risk areas, we found it on every place, object imaginable, from feed bins to barn keys to barn locks, barn handles, even rendering truck tires, rendering truck driver boots, in the entryway. We found it all over where a caretaker could possibly go. So the current mortality removal process protocol for Iowa Select Farms is they have designated mortality removal boots, which should be painted and are placed on the dirty side in the entryway and stored in a pan with Parasite disinfectant. All dead should be removed at the barn door and taken to the rendering box as the last task of the day. That should be the last chore for the caretaker. And the designated mortality boots should always be worn when taking deads to the rendering box. Barn boots should never be worn while doing this task. And caretakers, if they're using a dead cart, should always designate exterior dead cart, which should be clearly marked to take deads to the rendering box. They should never use an interior barn cart to do this task. And if using a tractor or other motorized vehicles, personal vehicle, they should change into clean coveralls and put on the designated mortality boots prior to removing the deads. And for sites using tractors, they should follow the path of least amount of contact to highly trafficked areas and avoid bringing tractors directly to the barn doors. And equipment that is used at the rendering box, snares, winches, etc., should never enter the barn. They should stay outside the barn. And obviously, the rendering box is a high-risk area for disease. So a shower is always required after removing the deads. That's why this should be the last chore of the day for the caretaker. And after removing the deads, the rendering box, coveralls should be placed directly into the washing machine prior to showering out of the site. And laundry should be done daily. So these are just pictures depicting where we found glow germ. As I mentioned prior, we found it glow germ on the barn key. We found it on floor mats, pedals, barn handles, dead cart. There's a trail going back from the rendering box to the barn. We found it everywhere the caretaker went. So, as I mentioned previously, glow germ was observed on surfaces ranging from rendering truck driver boots to pigs inside the barn, depending on what method was used. Maintaining a clean, dirty line with the removal equipment, showering after mortality removal, washing clothes daily, and having designated mortality removal boots were critical and preventing it from tracking into the barn. When caretakers were unblinded, they tended to follow protocols more prudently, which resulted in less spread than blinded caretakers. And standalone offices sites mitigated spread in the moderate and high-risk areas, as opposed to sites with offices within the barn. Offices within the barn tended to have more glow germ in the high-risk areas. And prior to the study, we asked caretakers what their thoughts were on the current protocol. And a majority of them suggested that they rather use booties over barn boots than the designated mortality boots. This study showed that when we're wearing booties over barn boots, glow germ was found inside the pig space at 67% of the sites compared to 17% of the sites with the separate mortality boots. So actually, separate mortality boots were more effective than booties over the barn boots. And the separate mortality boots had more spread within the site entryway within the low, moderate risk areas, but the booties caused more contamination from the hands and top of the boots, which was from the removal process. And personal vehicles generated a more considerable amount of spread around the rendering box, which equates to more being tracked back to the site offices compared to mortality carts and skid loaders. Glow germ was also found in personal vehicles, which is depicted in the pictures prior. And this is an issue because it has the potential of transferring to other sites if the proper clean, dirty lines are not maintained. So the results just show the importance of biosecurity. So current Iowa Select protocol is mortality boots should never enter a barn and should always be worn when taking carcasses to the rendering box. Never wear barn boots when going to the rendering box. This study showed that when wearing barn boots, this is what happens. You can see all the glow germ on the barn boots, and this introduces or has the potential of introducing diseases into the herd. The rendering box is obviously a high-risk area for disease, so a shower is always required after removing deads. This picture showcases a caretaker after he previously just removed deads. All the glow germ found on his hands, gloves, and coveralls. That's why you need a shower, because you have a potential contamination on the skin coveralls, which can be introduced into the herd as well. And finally, after the mortality removal process, coveralls should be placed directly into the washing machine prior to showering out of the site. These coveralls were not placed in the washing machine and were not washed. They were left out, and we were able to observe glow germ on the coveralls. These could potentially be used the next day, which can potentially introduce diseases into your herd. So that's why it's imperative to wash coveralls after choring. So the results showcase that having a separate mortality removal equipment, avoiding re-entering barns after removal, and wearing designated mortality boots were the best means of preventing pathogen transfer into high-risk areas. These findings also reinforce that if proper protocols are not followed, disease introduction might occur. So going forward, as I mentioned before, we found glow germ on rendering truck drivers' boots, on the rendering truck tires. So more needs to be done to investigate whether two-way rendering boxes, so the rendering truck does not have to pull onto the site, is an effective means of preventing contamination spread. There's also needs to be ways to prevent spread in vehicles, if that's the only option for caretaker, because that was the method that resulted in the most contamination spread around the rendering box. And booties in conjunction with designated mortality boots needs to be looked at, because booties in conjunction with barn boots was not affected, as that was the method that resulted in glow germ being found in the highest risk areas. So more needs to be researched regarding these methods. Thank you.
Our next presentation is by Rachel Patton from the Ohio State University. Rachel is going to talk about investigation of Lasagna intracellularis shedding by periparturient sows.
Hello, my name is Rachel Patton, and I am a third-year veterinary student at The Ohio State University. This summer, I participated in the SFIT program organized by Iowa State. I was sponsored by BI, and I was hosted by Carthage Veterinary Service in Carthage, Illinois. And this summer, my research focused on the investigation of Lasagna intracellularis shedding by periparturient sows. An introduction into Lasagna is that it is an obligate intracellular bacterium, meaning that it is required to live in a cell in order to survive. It is commonly known as ileitis, or porcine proliferative enteropathy, or PPE. It will cause the hyperplasia of cryptenterocytes, which can be seen in this image. You will note that there is a normal villi, and then there is the infected villi. The infected villi has an increase in the yellow cell type, which is an immature cell type, and this increase in cell will cause the thickening of the mucous membrane of small and/or large intestines, which will cause a garden hose appearance, which can be seen in this bottom image, and it should be noted that this intestine is very red and inflamed. Continuing, Lasagna has a fecal-oral transmission route, meaning that the sow will contaminate the piglet environment with her feces and therefore exposing them. There are two clinical forms of Lasagna. There is the acute form and the chronic form. The acute form has hemorrhagic diarrhea that can cause rapid death of replacement animals and animals that are close to market weight. The chronic form has much more mild diarrhea, and you will see poor performance growth in the grow-finished pigs. So, Lasagna is a worldwide issue, and it is primarily seen in grow-finished pigs. It has an estimated economic cost of $56.1 million per year in the US. So we noted that the existing data in sows in a commercial setting is very sparse and it is outdated. We were hypothesizing that if we utilized modern-day PCR, then we would be able to detect Lasagna from periparturient sows. We believe that the results of this study would directly influence the infection chain concept, vaccination strategies, and aid in the development of the whole herd approach. Overall, the objective of the study was to detect if Lasagna intracellularis is shed by periparturient sows. So this research included 3 distinct large commercial sow herds. They were between 5,000 and 6,000 sows. They were chosen based on their previous herd health history and their vaccination protocols. It should be noted that all 3 herds were supplied by 3 separate multiplication farms. So, 60 sows in a single weekly farrowing group were selected randomly from each herd. We went about this by I would arrive at the farm and ask the farm manager which rooms were actively farrowing. And so this was usually about 2 rooms, and I would go into the rooms and I would evaluate the sows and determine if they were within 5 days of farrowing. If they were within 5 days of farrowing and they had completed farrowing, then I would collect 5 to 10 grams of feces digitally from the rectum. And then, just prior to weaning, I would return to the farms and I would collect environmental samples. So these samples were collected between 15 and 22 days post-farrowing. And I would go about this by taking a gauze pad and I would wipe the farrowing crate floor and walls and really try to focus on the piglet dunging areas while trying to also include some sow fecal matter. Lastly, there were 60 sows that were randomly chosen in the gestation barns for serum collection. These 60 sows were different than the sows used for the fecal and environmental samples. The 60 sows in the gestation barns were chosen using a website called random.org, which would determine the row and the crate number of the sow that we would collect blood from. So the fecal and environmental samples were sent to Iowa State's Veterinary Diagnostic Lab, where individual quantitative PCR was used to detect the presence of Lasagna. Likewise, the serum samples were also sent to Iowa State's lab, where Lasagna ELISA serology was used to determine the level of herd exposure to Lasagna. Descriptive statistics were used to demonstrate the results, and Fisher's test was used to evaluate the difference between the sample type and herds. So this is a summary table of the fecal and environmental samples. As you can see, Farm 1 was the only one to have positive fecal samples, whereas all 3 farms had positive environmental samples. This table also includes the average CT and average genomic copy of the positive samples. At the bottom of the table, there are Fisher p-values, which were comparing the fecal and environmental positive samples. Farm 2 was the only farm that had a significant difference between those samples. This table is a comparison of the fecal samples between the farms. This data was determined to be significant, and this is likely due to the fact that Farm 1 was the only farm that had positive samples. Whereas when we compared the environmental samples between the herds, it was not determined to be significant. This is likely due to the fact that all farms had fairly similar positive samples when we ran the test for the environmentals. Lastly, this is a table of the serology. As you can see, all 3 farms had almost 60 out of 60 samples that were testing positive for Lasagna. And this is due to the fact that the replacement gelts are vaccinated for Lasagna. So there were some limitations to this research, and that was that Farm 3 was not washed in between the farrowing groups. So this means that the environmental samples that were collected for Farm 3 represent 2 sows. Additionally, since I was only able to collect from 1 weekly farrowing group due to the summertime constraints. So there are some implications of this research, and that is, should sow farms monitor for Lasagna? And if they do decide to monitor, how should they do that? Based on our results, environmental samples seem to be more sensitive, and this is because they represent about 3 weeks, whereas the fecal samples are only a snapshot in time. Additionally, should veterinarians require herd-wide vaccination of sows for Lasagna? And lastly, if the elimination of Lasagna is possible, then how far upstream would elimination have to begin? Like I said earlier, all 3 of these sow farms were supplied by different multiplication herds. So we can find it on our sow farms. Would we be able to find it at our multiplication farms? Overall, based on our research, Lasagna can be shed by periparturient sows and potentially exposed piglets. Exposure to piglets could lead to potential shedders and a source of Lasagna in later stages of production. And therefore, we must consider the sows as a potential link in the infection chain. In conclusion, I would like to thank all of my mentors and supporters this summer. I appreciated all their help throughout this project. And lastly, thank you to all of you for listening, and I look forward to any and all of your questions.
Our next presentation is by Zach Talbot from the University of Illinois. Zach is going to talk about the biosecurity box, investing in the future of your farm through science, innovation, and ingenuity.
Good afternoon, everybody. My name is Zach Talbot. I'm a 4th-year veterinary student at the University of Illinois. And the topic I'm going to be talking about today is titled Boxing Pathogens Out of Farms Through Science, Innovation, and Ingenuity. In order to bring items from the outside to inside the farm, they pass through a disinfectant and drying room. They're also referred to as a fumigation room. How we believe these rooms work is we get a shipment of items in. We believe that they have pathogens on them. So what we do is we place them on the wire rack shelving unit inside the D&D room. We then expose them to disinfectants emitted from a fogger. Depending on the protocol, it could be a variety of different times. After ran, we believe that these items are then pathogen-free and able to enter the farm. However, current research has shown that's not how these actual fumigation rooms are actually working. The research showed that only 50% of the items, or 50% of the surface area of the items, are able to be disinfected by the Hurricane Ultra 2 fogger. The study then took it a step further and ran 2 of them simultaneously, increasing the coverage by 10%, meaning that 40% of the surface area of an item and the direct path with the actual fogger and being disinfected. They then looked at hand spraying and showed that they were also not able to achieve full coverage, and it was also time consuming. And then another study showed that pathogen activation can occur over time. However, the humidity and temperature must be constant. And again, I want to reiterate that these were on items in the direct path of the fogger, meaning that items not in direct path of the fogger probably had a decreased coverage, even less than 50%. So some of the issues I've seen on the farms with the current methods, and we'll start with the Hurricane Ultra 2 fogger. They use a large amount of chemicals that are wasted. The reason being is because it's only contacting the items that are in direct line with the actual fogger. User error, meaning I've seen multiple times where the foggers are ran without the actual chemicals in them. It's not safe for employees' health. This is a huge issue because aerosolizing chemicals into a fumigation room, then you expect the employee to go in there and grab the items after they've been disinfected. However, although you usually have a fan in there, a lot of the chemicals are still staying aerosolized, meaning it is ultimately bad for the respiratory tract of the individual walking into that room. Hand spraying, you can have compliance issues, whether they do it or whether they don't. The employees' exposure to chemicals, again, respiratory and on their skin. PPE must be used or needs to be used. And there could also be cross-contamination during manually rotating the items to try to get full coverage. And again, the study showed that there was a lack of full coverage when using the hand sprayer. So I created a list of the different issues current that I wanted to solve, with the number one being employee safety while using chemicals. In order to increase compliance and create a work environment that's safe for the employees, I wanted to really focus on containing the chemicals and be able to get rid of them without the employees being exposed. Another thing was a lack of full item coverage with the disinfectant. I wanted to create something that has a chance to increase compliance, and also something that's easy, effective, and quick, and also reduce the amount of chemicals that are wasted. And to solve these issues, I created something called the biosecurity box. What this is a box that has doors on the dirty side and the clean side, dirty side being the outside of the farm, clean side being the inside of the farm, has multiple internal shelves, as you can see on the picture on the right, on the bottom, and in the middle here. And what it has is an internal misting system. This internal misting system emits chemicals 360 degrees around all the objects that are placed on the wire shelf. It's supplied by a water pump, and there's a built-in exhaust fan, as you see upper right picture. So all the chemicals are contained in here, and they're then emitted out of the room even before the employee comes in to remove the objects, meaning that this is a lot safer. Also, it can hold small and large items. And to make sure that this actually worked, what I did is I ran a trial, several different trials, and I was able to achieve full coverage of items in under 1 minute. So since I knew it worked with food coloring, I wanted to next take it to the next level and test it in a research setting on live pigs and actually objects being brought into a farm. So the objective of my study was to compare different fogging methods to disinfect PED-covered cardboard boxes before exposure to a pig bioassay. A little background of PED. It's a coronavirus causes a high mortality rate and morbidity. High mortality rate in piglets that are 7 days and younger. It also causes acute and severe diarrhea and vomiting. And multiple studies have shown that it's actually able to travel on objects for long distances and still be infectious. And again, this costs millions and millions of dollars for the industry. So the treatments in the study are the Hurricane Ultra 2 fogger, which I ran for 5 minutes, the ultrasonic fogger, which I placed inside the bio box to contain the fog and ran that for 5 minutes. As you can see on the video on the right here, the micron droplets are less than 5 microns, and you can see that they stay aerosolized longer, almost like a fog driving down the road. Next is a biosecurity box with internal misting system, and I ran it for 3 minutes. The reason I ran it for 3 minutes is because it's able to cover objects in under 1 minute. I just really wanted to put it to the test with the large amount of virus that we're going to use on the items. As you can see here, this is an internal view, and this is color changing paper. When it gets wet, changes red. You can see the quick coverage. The chemical that I used for this disinfectant study is called Decon 7. The study area was conducted in a BSL-2 facility with a central office and a shower between each room. Each different room, 4 different rooms with 5 pens individual, had a different treatment. For the bioassay, I used a total of 20 pigs, and they were 4-week-old PED negative pigs prior to entering the facility. They were fed an ad libitum non-medicated feed, and they each had an individual water cup. The steps of the study. First, I started with infectious PED infected intestines. I then mixed that with 20 milliliters of PBS solution and blended that up. Then I put them into a spray bottle. I then tested the spray bottle and it emitted 1 milliliter with each spray. The CT value of the PED stock solution was 10.9. So next I sprayed all surfaces of a box, 6 total surfaces, and the total PED inoculated per box was 9.89 times 10 to the 9. I then gave it 5 minutes of dry time. Next, I then exposed it to the different treatments, as I mentioned earlier. I gave it then an additional dry time after exposure to Decon 7 in the different treatments. I next used a sterile gauze pad and I dipped it in PBS solution. And what I did is I swabbed all surfaces of the box, and that material that I collected from the box, I then inoculated into the pigs. The reason I inoculated into the pigs is because of the next step, which is what I did is I placed this box that I had previously swabbed inoculated fluid into the pig to act as a fomite. And so if the pigs interacted with it, it was similar to if an employee grabbed a box out of the fumigation rooms, the method is currently being used. They then went to do the chores and interacted with the pig, therefore transferring PED. The inoculation was for consistency. To say if one pig in the group did not interact with the box, but the other ones did, that would not be as powerful of a study. So what I did for consistency is I swabbed all surfaces of the box, inoculated the material, and if any PED happened to be on the box, that means that the fumigation method did not work, then they would become infected. I also had control pigs. For 3 of the control pigs, they went through the same series of steps, minus the disinfectant exposure. And for the other 2, we inoculated 8 milliliters of the stock solution to make sure that the virus was live. So I did the chores twice daily, and we created a scoring system that was developed by Dr. Adam Mueller. And the reason I did this is because if a score of 3 was present for 2 days or more, the pig would be euthanized. Each day I assessed the demeanor, fecal score, abdominal appearance, vomiting, and plus or minus box interaction, that is fomite interaction. The results on day 5, the rectal swabs I submitted for PCR analysis showed that none of the pigs in the biosecurity box became infected with PED, whereas the average, again, these are numbers of the average CT values of all the other treatments did become infected with PED. And when we did statistics to show the p-value is 0.0003, that is comparison of the biobox versus the other treatments. So in conclusion, the biobox was able to inactivate PED below its infectious dose range, whereas Hurricane Ultra 2 fogger and ultrasonic fogger failed to inactivate PED on the cardboard boxes. The biobox also needed less time to inactivate PED and prevent infection in naive pigs. And this study also shows that infectious PED can still enter through D&D rooms if no disinfectant to pathogen contact occurs. That is, if you're using a current method, it's more than likely potentially happening. And lastly, from this study, we can conclude that investing in new methods and technology is crucial for producers to protect their farms from pathogens. I think we can all agree, as COVID-19 has taught us, you can never be too prepared for what obstacles may come your way. And when it comes to pathogens, prevention is key. With that, I'd like to thank JVI distributors for sponsoring the study, Carthage Veterinary Services for all of their help with the study as well. Thank you.
Our next presentation is by Rachel Weidmeyer from the University of Minnesota. Rachel is going to talk about the detection and persistence of Mycoplasma hyopneumoniae genetic material in environmental surfaces and the potential for cross-contamination of processing fluids.
Hello and welcome to my presentation on environmental detection and persistence of a Mycoplasma hyopneumoniae bacterin for the Morrison Swine Innovator Prize. Processing fluids has recently been discovered as a novel sample type for Mycoplasma hyopneumoniae. This is confusing since it's a respiratory pathogen, but the thought is since the epithelium in the testes is so similar to the epithelium in the lungs that could be why. Processing fluid has also been used to detect M. hyopneumoniae in endemically infected swine herds, as well as during a disease outbreak at a previously negative farm. It is still unclear where the M. hyopneumoniae is sourced from in our processing fluids. It's just unclear if it's environmental contamination, since the process PCR only tells us if DNA was or was not present. The objective of my trial was to evaluate the detection and persistence of M. hyopneumoniae genetic material in environmental surfaces exposed to a bacterin under field conditions. To do this, I selected a M. hyopneumoniae naive sow farm The sow farm was a positive pressure farm and a 28-day wean age. The selection criteria for my sampling areas within the farrowing room was based on location, temperature, and surface. This is a diagram of the farrowing room where I held my study. Wind would come in, air would come in from the hallway side and move through the room and exit the outlet here, which was one of my sampling areas. So the sampling area was based on location because we wanted to see how far it would spread within a room or the sow farm. So we had my sprayed farrowing crate here that I am circling, and we wanted to see if it would spread across a room, downwind into a different farrowing crate, downwind and out the sow farm, or up into the sow farm in the hallway or on the processing part. In addition, temperature was also used because it can impact the degradation of the DNA and M. hyopneumoniae survivability. So we had our high temperature areas, which were the heating mats in each of the farrowing crates, and the low temperature areas, which are all the other areas. In addition, we also selected based on surface. So we had the plastic areas, and we also had cement, which was just the hallway. The plastic areas was everything else, but we had our harder plastic here, and we had the softer plastic on the heating mat here. So I selected one commercial M. hyopneumoniae bacterin. That the bacterin CT value was 16.52. And just as a reminder, the lower the CT value for PCR means the more concentrated a sample was with DNA for that test. And I sprayed 1 milliliter onto the heating mat in my selected farrowing crate. To spray my vaccine onto the mat, I selected a 12-inch tall cardboard box, which I lined the inside with plastic so that when I sprayed the vaccine, it would not be absorbed. None of the vaccine would be absorbed by the cardboard, but would instead flow down into and towards the heating mat. This is what I use to spray my vaccine. I would put the vaccine in the syringe bottle holder here, and I would use a spray tip nozzle to spray the vaccine. And this is a picture of how the vaccine would have been sprayed onto my heating mat. As you can see, a little bit more concentrated in the center and not as concentrated towards the outside. Now, the area that my vaccine was sprayed was broken into 8 equal segments because we were testing at 8 different time points. We tested at day -7, which was just to prove that the area that the sow farm was negative for Mycoplasma hyopneumoniae. And then we also tested at day 0, 2, 4, 7, 14, 21, and 28 days. Now the only area I sprayed was the heating mat in that one farrowing crate, but I did set up this similar sampling area in all of my locations. And this was the swab I used when I was swabbing the areas. And over here on the right is a model of how I would swab each area. And I took the temperature using this infrared thermometer over here right after I had finished swabbing the area. And this is the diagram showing the results of our trial. Right here where I'm circling with my pointer is where the sprayed farrowing crate was. The processing cart, the hallway, the farrowing crate's heating mat across from the sprayed farrowing crate was, and the outlet were all negative at every single day. Now the only sites positive, we had the heating mat in the sprayed farrowing crate, and we also had the sow feeder area that was also positive during some days, and we had one positive result in the downwind farrowing crate's heating mat at day 7. This is a graph of the temperature and bacterin detection by PCR on my sprayed heating mat. The orange line would be the temperature when I took the samples, and the blue bars would have been the CT value for the PCR. Now just a reminder again that the lower the CT value means the more concentrated the sample was with DNA. So as you can see, it starts off more concentrated here and then generally tails off to be less concentrated with higher CT values. And as you can see here, represented by the orange line, there's no correlation between temperature and the CT value from the PCR. This is a graph of the temperature and the bacterium detection by PCR at my sow feeder area. Again, the orange line is the temperature that was taken at the time of the sample, and the bars are the CT values for the PCR. So initially you can see the CT values for this area were consistently higher than the heating mat. And it's unclear here at day 714, at 7 and 14, if I just missed the bacterin or bacterin was so low that it did not result positive here. So from this study, we can infer that the bacterin can remain in the environment for the full length of a farrowing room's turn, and the bacterin can be spread within a crate and possibly within a room. Just some important considerations for that the piglets in my sprayed farrowing crate were removed at day 4, and the gilt remained in the crate until day 21. So it's unclear how the piglets could have further affected this study, if they could have degraded the bacterin faster, or if they could have spread it more within the room. Additionally, only one commercial bacterin was used. So some future research, obviously more replications of this environmental trial need to be done. The point of this study was just a proof of concept. We wanted to make sure that the bacterin can remain in the environment long enough. Additionally, testing processing fluids and other sample types with the bacterin sprayed in the environment. So we showed in my study that it can remain in the environment, but now we need to show that the bacterin in the environment can contaminate sample types for Mycoplasma hyopneumoniae. In addition, we just need to test more commercial bacterins, since each bacterin uses a different adjuvant in its vaccine, and adjuvants can affect how quickly DNA can be degraded or the vaccine can be degraded, or it can improve the stability of it. So just more bacterins need to be tested to see how the adjuvants affect it. I would like to thank my mentors, Dr. Deborah Murray, Dr. Levi Johnson, Dr. Amanda Sponheim, Dr. Maria Peters for assisting me in developing this trial, as well as the Michael Lab at University of Minnesota and the Sow Farm staff for assisting me during the trial itself. Thank you.
And our last presentation is by Allyson Witt from Iowa State University. Allyson is going to talk about evaluation of a 360-degree camera as an adoptable precision livestock farming technology for use in providing commercial swine veterinary care.
Hello, my name is Allyson Witt, and I'm a second-year veterinary medicine student at Iowa State University. This summer, I had the opportunity to work with Dr. Dale Polson at BI, and we investigated the use of a 360-degree camera for commercial swine veterinary care. So currently, our industry has a few hurdles, one of them being that smartphone cameras that are being used have a limited field of view, that being only about 80 degrees to 120 degrees. And of course, what is being recorded is what the recorder deems important, not necessarily who is watching it or the audience. So what the audience might pick up or think is important is definitely different than what might be being captured. And so there's a potential to miss out on important information. Another hurdle is that, of course, we want to keep our pigs safe, but because of this, we have to limit the site visits between farm personnel for biosecurity purposes. And this is a little difficult, especially with high turnover rates. So there could potentially lead to a gap in monitoring for weekends, holidays, and then because of that, there could also be a delay between onset of clinical signs, detection, and then implementation of treatment if necessary. And so a new hurdle that we've kind of had to figure out is that we are now trying to limit numbers of visitors per farm site due to COVID to keep our farm personnel safe. So we set out to say, how can we overcome this with innovative solutions? And we thought that a 360-degree camera could answer some of those problems. And so you can see there are a few different options of 360-degree cameras on the market. We went with the Insta360 So a little bit more about the camera is that it connects to an iPhone or Android app or on a tablet, and you can control videos, photos, and also settings through the app, but you can also control these things on the camera itself. So the camera does have an SD card, so you are able to use the camera without using the app. And then it's important to note that it is waterproof up to 5 meters, and it's relatively lightweight, and it is microphone adapter compatible. And there is also a life-proof case that you can use with this as pictured below. And so what we did is we went into the farm site, recorded the video, and then once we were off site, we were able to upload it to the app. And then through the app, we were able to send a private link to anyone who can view it. And so only if you had the link could you have access to the video. And so this is what it looked like when you access the link. And so you can see this is an example of perhaps a caretaker doing a pen walkthrough. And if I was a veterinarian, I could be viewing this from my office or another remote site. And the great part about this is that I have the ability to specifically look for things that a veterinarian would be interested in. So I'm looking to see how active the pigs are. You can see they're all getting up just great. And also we have the capability here to pause if we need to and take a look at feces or manure just to see if there's any scouring. And also we have the ability to look completely up, completely down, and different ways. And then another option here is we can pause right on the feeders to see that feed level, which this is something that, you know, a caretaker may not think is very important, but to a veterinarian, we have a different perspective, and that could definitely be vital information. So how can this be of value to us? And so as demonstrated, you can do pre-recorded on-site visits and then sent through a private link to a veterinarian or any referring veterinarian, anyone else, third party outside, not on site. And then also this company creates a camera, not this one, but one similar technology that has the ability to live stream through a third party platform. And this is at no extra cost. So between those two options alone, this is a great option to help triage emerging diseases, specifically foreign animal diseases. So if a managing veterinarian were to see this, they could potentially decide if this novel disease needs to be reported to the USDA before they report on site to check it out themselves. And so this also helps establish the veterinary client-patient relationship and keeps record of that. And along with this, it's also a visual documentation so that in the future or even past cases, people on the farm can compare and really decide if this disease or health issue is recurrent, persistent, or emerging. And then along with that, some value is in that it can be offered as an SOP training solution. So whether that be onboarding information to new hires or an update in procedures and notifying personnel, this is just another way of helping with that education factor. That 360 degrees really gives a unique view of whatever information needs to be relayed on, and it really offers a solution to that limiting standard view. And also there is a software development kit option with this camera and using this company. And so if as a farm or any health organization you use an app, whether that be to record mortality, feed consumption, anything like that, what you can do is you can use and integrate this camera into that app. So instead of using their app to control the camera and to take videos and adjust settings, you can do that through your own app yourself. And so we wanted to really hone in that this does not replace standard management practices by on-site personnel, but it can enhance the overall animal care. And so a few things for further implementation, before we can get to further implementation that we need to develop, is that we need to obtain producer, consultant, and veterinarian feedback on applications and use cases. Also, we need to establish data security and confidentiality standards, as well as defining bandwidth requirements on site. Of course, we'd like to see some ROI projections, as well as perform some durability tests to see if it can really hold up with the harsh environment of a pig farm. And also it has the potential to be a fixed mount camera, so that a person does not have to physically hold the camera and walk through the pens. It does have the capability to be fixed in place to kind of help out or be able to better utilize the live streaming feature or the remote access. So all of those are a few things that need to be tested out a little bit more before this can be used in farms. So I just wanted to say thank you to Dr. Polson for this summer, and also for James Rudy at Summit Smart Farms for helping me with all of this. Thank you.
Thank you to all of our speakers. And now we will open the floor for questions.